Looking at projectile motion in 2 dimensions, and this is again review. What we mean by projectile motion in 2D is that there's an initial horizontal component to the velocity, and so it's moving sideways to begin, maybe up and sideways or down and sideways or just sideways, but there is an initial x component. So that does change how we solve the problem, and we use x and y components to end up solving. One thing that we make the assumption every single time, unless it's sort of a thought experiment or sort of a word type answer, but not with math, is that there's no forces in the x direction. We're assuming there's no air resistance, so the thing's got the same x component of velocity the entire time. However, so the x velocity is like a uniform motion problem almost. In the x direction, sorry. In the y direction, it's a 1D projectile motion problem. So there's like 2 problems going on, and that's how you solve it, with 2 problems. It's like 2 questions, two sets of equations. The thing that's constant between the x side and the y side is the time that it's in the air. Okay? Just, what's going on. I love this little graphic I found that if you look at the initial, this would be an example of the initial velocity. Now, it doesn't have to be up on an angle. It could be down on an angle, but we're saying it's up on an angle. So here would be the initial x component of velocity, and this is the y component, right? And if we just keep looking all the way through, this is what I mean by A, B, C, D, F. If you look at every stage of the throw, from the time it's thrown to the time it hits the ground, the x vector never changes. It's constant, and that's what that represents. The y vector, however, if you look at it, it gets smaller as you go up, which you can picture. At the top, it's got no y component to its velocity. The only velocity of the object at the top is its x component, which is the same as throwing something straight in the air. There is no x component, but there's 0 y component as well. And then you see by the change in the direction of the vector that it starts to accelerate in the down direction, right? It's actually accelerating in the down direction on the way up as well, but by slowing down. And then on the way down, it speeds up, and you see the vector gets bigger, right? And that's really what's going on. And now we just have to apply the mathematics to that. So write down what you need to here, and as I've said it a few times, you treat this problem as 2 questions, where the time is constant in between them, right? So the strategy, just to look over here, is you take either the x direction or the y direction. Where you can, given the information you have, you solve for time. And then you can carry the time over. If you've solved it in the x direction, you can carry the time to the y, or vice versa, right? The things that we know for sure is that Vx doesn't change. So if you know the initial Vx, it's going to be the final Vx. It doesn't change. It's really a uniform motion problem in the x direction, where this is the equation. Okay? Distance equals speed times time, really, just in the x direction. In the y direction, the y acceleration never changes, and you can use any of these formulas, any of these accelerated motion formulas. In grade 11, I always use this one right here, and this is the most common in this course as well, but you will see in your assignment, or I think in one of my examples, that we're going to use one of the other ones, and you can. Okay, it doesn't change anything. It's really a one-dimensional problem in the y direction. Okay. So the example I'm going to show you is the easy example, and you definitely did this in the grade 11 course. We're saying Peepaw here is driving his lawnmower on his neighbor's lawn, and he hits a little cliff, and he falls over a 2.1 meter cliff. Let's imagine he lands on his lawnmower still driving, and he doesn't fall off, and he doesn't tip. So his speed, just as he leaves the cliff, is 4.5 meters per second. So he's driving along at 4.5 meters per second. He's moving horizontally, and then he falls 2.1 meters. That's his dy. And we want to know how far here, what's his dx. And you can't see it very well, but I did make a sad note about what a bad job I did drawing that's supposed to be sort of half of a parabola, but anyway. So the things that you do, right, when I say good form, choose a positive direction, usually, especially in these easier examples, usually it's, direction of motion in the x direction and y, down. Draw a picture, list everything you know, and make a table. Okay? So if we look here at the table, I've got in the x direction, I usually right away just write that formula because that's the only one that's going to apply. Last year in the y direction, I would write down this formula at the very top. but it doesn't always apply this time. So that's why I'm not starting with that. We write down the thing we know, that Vx is 4.5, and we're looking for time. And really we don't have enough information because we don't know dx and we don't know t. So there's nothing else I can do on the x side of the equation. So looking at the x side of the table. On the y side though, I know my acceleration, it's positive because I said down was positive. I know my dy, again positive because it's moving downward and down is positive. Has no initial y velocity. And the idea is if I know three things, which I do, I can find the fourth. And the fourth I'm looking for is time. So just going through the rearranging process, right? V1 is 0, so this whole term is 0, right? That whole thing becomes 0. 1/2 of 9.8 is 4.9, and then t is what I'm looking for. So rearrange, solve for t, 0.65 seconds. So that's how long it takes Peepaw to hit the ground, and then I can just put the thing over there, sub that into the x side, okay? And solve for dx. So that's an easy projectile motion. In the next video, I'll do a hard one using some of the other formulas.